Hello and welcome back to our next iteration of the project to implement the Ray Tracer challenge by James Buck in Rust, a language quite new to me.
Hello, just a short intermission from a little bit wiser and older Jacob, which by now has done some of those recording sessions and some more streams, and has realized he forgot to tell you that there are information in the description below regarding the GitHub repository where you can get all the code we are writing here to follow essentially along. Furthermore, please bear with me while I'm still learning on how to present all the different things I'm doing currently during the recordings. I get better from recording to recording, from session to session, so please be a little bit patient. And now, back to the program. Have fun.
Where were we the last time? We finished more or less chapter 2, which was implementing canvas, which could hold different RGB colors or pixels, to be more precise, and then an implementation to export those canvases. What's the plural of canvas? I don't really know. To a file, to a ppm graphic, especially an ASCII format version of this graphics format, in order to render something to our system. We have written tests for it. We have ensured that everything works as it is intended, at least with regards to the book. It was a little bit of a hassle to get all this to work, because first I misunderstood what the book wanted from us, or the author wanted from us, and then we had some problems with Rust. Problems as in I didn't know certain things about Rust, but that's fine because I'm still learning, or we are still learning. So let's start to ensure everything is still in order and still working out by running all the tests. And as we can see, all our tests, which are 37 at this point, are running fine. So great. The next thing would be to put all of this canvas stuff in addition to all the stuff we implemented before, the tuple stuff with vectors and points and stuff like that, to work here. And we do this by copying our last chapter entry point, because now we have a second one, but it's essentially based upon the old one. So we've now copied this. We can close this one. Let's clean up a little bit and close some of our files here, because we don't need them anymore at the moment. And let's take a look at what we are going to do. What we are essentially planning on doing for this session here now, to put all this stuff together, is to have the same example as before, which is a projectile which is kind of fired somewhere, and we want to now, instead of just dumping out the coordinates in the console, we want to plot those projectile paths, which are actually calculated into a graphic. So what do I mean by this? Let's do this one, and let's how can we, now we have two executables, how do we run a specific one? I guess we can specify it with bin. Yeah, bin chapter 01. So this was the first example we used. We have a certain environment with a gravity and wind velocities, and we have our projectile which starts at a certain position and with a certain velocity, and then the gravity and the wind are applied to it for each of the different ticks until it reaches ground by hitting or going below the y-axis. So essentially we want to plot out all of these different steps here into a graphic now. So first of all, we need to take into account that the coordinate names or the coordinate space of our canvas is quite different to our vector coordinate space. So in our vector space, we have all those floating point numbers, but in our canvas space we actually only have integer addressed pixels. So we need to somewhat convert between those. Sorry. And furthermore, we have to take care of that the canvas coordinate space is has an inverted y-axis, as we are starting essentially. Wait a second, this image is mirrored. So we are starting at the top left of our picture with the y-coordinate of 0, and then we are actually wandering down with y, whereas our usual world coordinate space, we are calculating all this stuff in here, starts with the y with the 0, 0 just down in the bottom left corner. So we have 0, 0 here for our canvas space and 0, 0 there for our world space. So we need to somewhat convert between screen space and our world space, which we need to do in order to plot this. So yeah, let me quickly just glance over this chapter again, because it's now a couple of days since I read it. There is an example here with a certain amount of like the starting point and the velocity and the wind and gravity values, which actually produce a nice ballistics curve of our projectile, which we then can play around with. And I would suggest we start with that, just to have something we know should be the output. And I will do that now by instantiating a new environment here, which has actually what is it? Gravity is like the one I defined. The wind is actually this one. The starting point of our projectile is, yeah, that's okay. And the starting velocity actually is 1.80, which is then normalized and then multiplied by 11 and a quarter to give it a certain speed. So this actually defines the direction of the vector, and this gives, and then normalize ensures it has a length of 1, and then we multiply it with 11.25 just to give it a certain force behind it for a velocity vector. So by the way, I'm still not 100% sure that this is the way one is supposed to create structs in Rust by always using and creating this with a new function, because I'm thinking about, like, if we just comment this out for a second here. Wrong keyboard shortcut. So if we have an environment here, which would be defined like this, where we then have like gravity is a tuple. Okay, now there we need those kind of shortcut functions, but that is fine, I guess. So let's just, I know this is not the right syntax, but and we have wind equals another tuple, which is a vector. I think I kind of like this better, because we now see the naming behind this, and we directly see this is the gravity vector and this is the wind vector, and there is no special initialization going on here. With this one, with this vector, there is special initialization going on because we are setting the W value. But with the environment, for example, it's just a data container which does not have further information in it. So I guess if there is a new function, we should definitely use it because we don't know if there is special initialization going on, which we need. But on the other hand, I'm not sure if this kind of simple data container structures are supposed to always be instantiated with this new function we have implemented for everything. If you have certain information about that, please leave some of that in the comments. So let's take a look at this, because everything I can find on the internet about this is that it seems to me the new function is the new best practice to do it, but there is a lot of code on the net where it isn't done this way, and it's done by the usual struct initialization, and I'm really not sure which one is the one we should use. What is the best practice here? Sure. So if you are a little bit more versed in Rust, please tell me. Okay. So now that we have this these values here, which are proposed by the book, let's run our first chapter again and see how many steps there are. There should actually be a lot more steps before we are hitting ground. Oh no, there aren't. Oh no, I ran the wrong chapter. Let's run chapter 2. Okay, and there is a... What did I do wrong here? I have a non-floating point value there. So let's compile this. Yeah. And so there are now 198 ticks before we reach actually the bottom. This is actually quite nice because this seems to be a quite nice trajectory. We have a Y, which is it's going up and up and up and up and up, and somewhere there should be the point where it starts going lower again. So it's getting slower and slower and slower and slower and slower. Here, as we can see, it's reaching its peak and then it's falling back to Earth due to gravity. And X is simply a ballistics trajectory along the X-axis. That's kind of I like that. So it seems to me that those are quite interesting points. So yeah. So now we actually want to change this a little bit in order to create and render our graphics. Yeah, let's initialize a canvas here now. We now have implemented this canvas. Should be canvas new, and let's take a look at these values and see what kind of canvas size we need. So we have this X here, which has a maximum of, what is it, 883. Maybe we should then have a 900 width or something like that. So we could actually accommodate all of this stuff. And then what is the maximum Y we get before falling back? It's around 500, maybe 900 by 500. We could try this, I guess, because I guess it's the max. I don't see anything beyond 500. So let's try this. Let's initialize a canvas, 900 by 500 pixels. Then let's print out the environment. We are now issuing our tick function, which does the calculation, which is actually updating our projectile's position by its velocity and the gravity and stuff like that. So at this moment where we are printing the information, we want to actually draw something within our canvas. So what we want to do here is we want to Do we have imported canvas here? I don't think so. No, we didn't. So let's get the canvas here, because otherwise we can't even do this. And maybe we should set our let's define a color here as well, because we need a. Why don't we get completion for that? There's something broken again with my IDE. It seems to. Let me restart this. It seems to me that there is a problem with my IDE. If I leave it on for too long or let the laptop go to sleep, then there somehow, yeah, somehow those error messages go bonkers and aren't there. It seems to me that the language server, which does give me all this information about the Rust compiling in the background, doesn't work then anymore. So, okay, it doesn't know how to resolve canvas. Yeah, that's because an N is missing here. And there you can see how important IDE and compile warnings and information are. So now we should have all this stuff. Let's define a color for our projectile. So I guess we are simply doing color new here. And what kind of color are we using? Let's use, I guess, why not? Let's do red and green together. And let's, no blue component. So now we should have a yellow. And now, of course, those variables are still unused. So now we are going to implement something here, like we want to have canvas right pixel, which will actually not work because our canvas is not mutable. So we need it to be mutable, please. And now what we are doing here is, okay, I will add a struct here called pixel, and it has a y, which is a u size, and an x, which is a u size, and a y, which is a u size, and yeah. So impl pixel. Or let's call this. Maybe we can even use this later on. Let's call this screen coordinate, and we have a screen. We have now an implementation for screen coordinate, and I want a function here, which is called from point, I guess. From point. So what we have here is we are getting a tuple now. So let's call this one point. It is a tuple, and it will return a screen coordinate. I don't like this name, screen coordinate. Let's call it pixel. A pixel is always something that's on the screen. It should be implied that it is in screen space. So yeah, let's do this. And so we can do all our, we have now a structure to even store our information. And further along, we have a function which is able to convert between a tuple and a point and a pixel. So the first thing we need to do here is we need to check if point is point. And if it is not, we are actually panicking here and saying given tuple is not a point. Point needed for conversion to screen space. Because we want to ensure that that we only can convert points to screen space because converting vectors to screen space doesn't make sense at all. So if we are doing this at some point in the future, I don't want it to be allowed actually. So we can, because that would be a bug, and we therefore can easily see that we have a bug there before even searching for it a long time during a debugging session. So okay, now we have this from point stuff here. So we can actually calculate it. What do we need to do now? Let's write this out. First, we need to, yeah, I guess convert from floating point space to integer space. That's the first thing we need to do. And the second thing we need to do is invert y-axis to fit canvas space, and there we have a problem. We don't have information about the canvas space, the screen space here. So I guess this operation needs a screen space essentially. So by the way, this is supposed, no, not to be public, but this is supposed to be public, I guess. So yeah, the problem is that we don't have the canvas space here. But let's take a look at the first things first. So we can convert from floating point space to integer space. Okay, so let's have a comment here. Completely ignoring z order and z value for this now. So yeah, so let's just convert this, I guess. Let x, which is a usize, be the point dot x dot round. So we are just rounding it to the nearest integer, I guess. So this one rounds and still gives us a floating point. Oh, okay, it gives us a rounded floating point. So if we now convert this to a usize, it should actually cut off all the decimals, and we should be fine here. So let's do the same thing for y. So now we have this rounded integer values we need. And now we actually need to invert the y-axis to fit canvas, or better said, screen space here. Let me comment this as the coordinate, as the 0, 0, 0 coordinate is top left and not bottom left. So we have this here, but in order to do this, we need to know how high our screen space is. So we actually need the canvas here from point for canvas. Let's call it this, and then we give it a canvas here, which is a reference to a canvas. And in order to now calculate this, we are doing let inverted y be, we need the canvas dot height minus inverted y. No, minus y. And this should give us the correct coordinate there. The x coordinate is not touched. And now we can actually create a new pixel, which is x and y inverted y. Let's call this screen mapped y, I guess. So now we should have this transformation, mismatch types, yeah, because there is a semicolon again. And now now we have this function from point for canvas. So now what we can actually do is we can let pixel, or let coordinate be pixel from point for canvas, and we simply give it our, where is it? Current dot position, that's the point, and we give it we give it a reference to our canvas, and there is an R missing, so yeah. Now we have this coordinate, and we should be able to simply use coordinate dot x, coordinate dot y, and our before defined color to write this pixel out. And there we have it. So essentially now our canvas should be properly filled, and the next thing we need to do is we need to write or export it as a ppm somewhere. How are we actually doing file operations with it? Let's just, I know it's going to look awful, but let's just print out the ppm, the canvas. It will be a lot of things, but we should be able to see that there are a lot of zeros and certain values there, just to ensure we have the right thing here. And then we take a look at how to actually store a file with Rust. So yeah, let's or how we are accessing the file system, because I don't know how to do that yet. So we have a canvas here, canvas, and we have this 2 ppm actually. No method name 2 ppm found for struct canvas in the current scope. Wait a second, we have a 2 ppm function, don't we? I guess we've called it 2 ppm. 2 ppm. Oh, it's I implemented it in a trait. Okay, so okay, so let's first try something different. Let's do a let ppm equals to canvas dot 2 ppm here. So won't work as well. So, but let's split this. No method 2 ppm found for struct ray tracer canvas, which is, it's kind of strange because the system seems to know that this is the right type. It is the type canvas. I don't really understand why it now can't convert this. Oh, outside the world is just it's kind of gone. It's raining that hard that I can't even see outside anymore. It's just like the world ends before the window, after the window. So let me just quickly check if I've closed all the windows here before I'm knee deep in water. Be right back. There I am, back again. Nothing got wet. I closed all the windows at the right time. Okay, so let's take a look at, where were we? We had this problem with the ppm not being able to be called here, the 2 ppm function, and we weren't sure why. Yeah, and I'm still not sure why. So in this test, it is working. And the test is essentially in another module, which includes all of the above. Do we somehow need to include the trait? But I guess this should actually, the trait should be included here by including everything from this namespace. Maybe, wait a second, did I not make this trait public? I did not make this trait public. Is this the reason for it not working? Okay, so yeah, that makes That makes absolute sense. If I don't have this trait in a public way, I can't actually use its implementation anywhere. That makes absolute sense. So let's just commit this little change here. Source canvas git ci mate 2 ppm. There we go, 2 ppm. Trait public to be used by other parts of the application. Yeah, so, and now we should actually see if we do cargo run --bin chapter 2, we actually should see a lot of pixel, a lot of, oh yeah, this is actually, this is the vector with the vector with the bytes in it, the ppm bytes. But are there only zeros and spaces? There should at least be some values in it. Okay, I don't know yet. So maybe let's just, so we are getting information there. Let's just check on how to write this to a file. So let's go like Rust, write to file. stdfs. Sounds kind of what we are looking for. So use stdio write. Wasn't it called stdio write? stdfs write. fs write. Yeah. So now we want to use this. Instead of printing, we will do a write path. I hope we can do something like output.ppm. And we want to write, what is it getting? It is a U8 slice. So actually we should be able to just put the unused std result that must be used. Ah, okay, it's that error handling stuff. I need to quickly read up on that because I've only skipped over it. I guess it's recoverable errors. Yeah, it's this result data type which is given back. And oh, there's an example with a file. Nice. Yeah, we can do this matching style, but there were other possibilities, like shorter versions, like we could do something like simply tell it to panic if an error occurs. Oh no. Yeah, exactly. We could call unwrap on it to just ensure that it is an okay, but we could use this expect to have a more precise error message. So what we want to do here is an expect could not write output.ppm to disk. Something like this. Yeah. Now let's try and run this. And it seems to me maybe we have an output ppm here. What happens if we run it again actually? It will be written again, overwritten, I hope. 2.6 megabytes. That's quite a large file format. So yeah, it stays at 2.6 megabytes. That's quite nice. So let's just inform what we are doing here. Print line, writing output.ppm. So, oops. So that we don't wonder what takes up this time there. And I think it's kind of slow, but everything done. Maybe okay, let's kind of take a look at this output and let's see if there is a picture actually in it. There is a picture in it. Wait a second, where is it gone? There it is. So actually, we just processed the information correctly, and yeah, and have this nice trajectory of our flight path. So, but let's actually take a look at the data. Yeah, this is the image format, and this is what I meant. It's kind of interesting to say at the least, because this always is one line of data there, and there were some pixels within it, yellow pixels. Okay, it's a completely strange image format, but it's working. It can be displayed and it's working out. So actually, I kind of like that. It's abstrusely verbose, but it's working. I like that. I like that. So if we, for example, now introduce a lot more wind, let's say in the x direction, let's say we have 0.07 here, we should get quite a different output path. So yeah, so so now I like that. So now we are actually throwing this thing outside of the of our trajectory here again by having it leave its path and being blown back to the left side. Okay, nice. But what I find quite interesting is that that this shouldn't actually have worked, I guess, because what we didn't do yet was make sure that the pixels we are printing are inside the canvas space. Essentially, this here is Rust. We are using usize, so unsigned values for our data. Is Rust automatically making a conversion between a signed value and an unsigned value 0 if it's below that? Doesn't it overflow into the other two complement variant of the number? That would be strange, because that would imply that it does this checking for every assignment. I wouldn't expect that, actually. So let's take a look here at what is actually happening. Where would it be happening? Here. So let's just print line, just for debugging purposes. Let's do something like that. Let's call it screen so that we see it immediately, and let's put in X and Y. No, actually that's not right. So let's put in X and screen mapped Y, so that we should be able to see this when output. So it's actually just as it is getting negative here, it is indeed 0. So this conversion actually is kind of type safe. Otherwise, this would have done kind of strange things, like coming back in from the other side of the screen. Maybe no, it would have done a lot worse. It would have actually crashed our program or written into memory that it shouldn't have even accessed. Yeah, it would have been bad. So thanks Rust for saving our ass here, but On the other hand, this means we need a way of kind of telling that we are outside of screen space. Maybe we could do this by using an enum instead of a pixel. Let's do a pixel enum. And let's then do a coordinate here, which is a struct. I'm not sure that there is a possibility to have these inline structs, but I'm not sure that they are actually done this way. Is it this way? I guess it's this way. No, it's not this way. So I need to read up on this, and maybe I could do something like out of bounds here or something like this, and then I could return a pixel. Let's just wait a second. Let's just take a look at this enumeration. Defining an enum. There it is. So there is actually this, and you can define it yeah, like this, but you can define this stuff inline somehow. So this is just with values, but I want it with a struct inside. Okay, it's just like you define it like this. I get that. Makes kind of sense to me. So so this should actually do I need this? No, I don't need those here. So now we have either we get a coordinate or we get yeah, so now we do something like is it coordinate here? Do I write it? Do I write it this way? Can I just do it this way? Okay, so this is actually working, but first I need to check if point point x is bigger than I don't know if I can compare it this way. Most likely I won't be able to compare it this way. Let's check if we can do this. Canvas.width. Can I do this? Okay. Or point x is smaller than canvas dot no, it's smaller than 0. It's less than 0. Or point y is bigger than canvas height, or point y is less than 0. Then return pixel out of bounds. So now we get the type mismatches. Great. So yeah, so what we need to do first here is I can remove this, I guess, because I'm statically casting. So let's call those x, or let's call those ix and iy, because they are now integers and I need them somehow, and let's have them. Is it called isize? Yeah, it's called isize. Did I just delete this if, and now I can now write it again? Great. So let's do an if ix is smaller 0, or iy is smaller 0, or ix is bigger than canvas.width, or actually canvas with if it's bigger or equal, actually, because the pixels are 0 indexed, and if this is bigger or equal canvas.height, then isize and usize. I need to do this in with different steps. If ix is smaller 0 or iy is smaller 0, then return pixel out of bounds. Yeah, so okay, we can remove this parenthesis here, as we are now sure that this. I don't want to do this actually. Can I ask is there a way of, is there point is negative or point x is, there is. Okay, so what I actually want to do is, if I'm rounding a negative value, it can never be, no, that's not true. A rounded negative value could actually become a 0. So we need to round this here. So let's call this Rx and Ry and simply round those values here. And we definitely want let Ix Rx as U size so Ry as U size. So now we can do this in one thing. We can ask it point x. No. Rx dot is negative, or Ry is negative, or Ux is bigger than canvas dot width, or Uy is bigger than canvas dot width, height. Come on, height. Then we want to return pixel out of bounds. So now we can remove this, and now we call those screen x actually is x, and let's, no, it's ux, and screen y is uy, and then we put this one here and tell it is screen x, and this is screen y. So now we need to change the usage of this, because now now we are pixel from point of canvas. So let's do, how was this match working? I guess it was like, let's call this pixel then. No, we can actually do it. I didn't want to do this. I just wanted to put a match before this and then do it like this. And then was it like simple coordinate coordinate chord, I guess. And then we could have something like out of bounds here, which would actually do nothing. And this one would then write to the canvas. Cannot find tuple struct or tuple variant coordinate in the, you can't pixel coordinate, but it's there. Do we need to do this? Expected tuple struct or tuple variant found struct variant pixel coordinate. Struct variant? Wait a second. Have I done something wrong here? It's now an enumeration. It's called pixel. And I've got this coordinate thingy here, and I need to take a look at this. Okay, so isn't that actually what we did? Isn't that actually exactly what we did? Even though I may have needed to, no, I've prefixed it with pixel, but I needed to prefix this one as well. So is that the problem? No, it's not. Expected tuple struct or tuple variant, found struct variant. So, coordinate. So this does not work for us. Why doesn't it work? But we called it. But we okay, is negative, is not use of deprecated associated function is negative. Rename to is sign negative. Okay, so we can do this is sign negative is sign, oh, is sign. Is sign negative. So we don't want to use anything deprecated. But we now have this coordinate here, and it has this implied struct here. So how can we, or do I need to do it like xy maybe? No. Can I, maybe I need to do it like this? No. I don't understand this. Because essentially they are doing the same here, aren't they? I mean, in this case it's not a struct, so maybe I need something more elaborate here. Matches are exhaustive. Yeah, we need to always define any match, or we have this. That's actually the same as with most pattern matching languages I know, like Erlang or stuff like that. So I don't right away get what I'm doing wrong here. So maybe we want to Google that. Enum match anonymous struct. Destructuring should work here. I don't really understand how this is working actually. So if I do now, it's okay. Do I need something like this? Is this working maybe? No, it's not. So is this working then? Okay. So I can get these values just out of there. Okay, that's okay for me. I can live with that. I see, because usually in the matching process there are tuples, and now I have an anonymous. I get it. I have an anonymous struct. So yeah, okay, that's something to remember. So if I wanted it to be named, I would really have to define this struct outside and then use it inside there, which would kind of make sense, I guess. Yeah, okay, I get it. Yeah. Okay, so now running this should actually, there was a warning. What kind of warning was there? Help, convert the identifier to snake case from, oh yeah, definitely. Bad habit from other languages I'm usually working in. Where's my rename? There's my rename. No, rename symbol, which isn't working for some reason as a keyboard shortcut. From point for canvas, and I definitely need to fix this at some point, but especially when we are going to refactor some code, which we didn't that much yet. So let's compile this. Okay, no warnings, everything done. Writing output. Let's take a look at this output. Where's this? Where's my output gone? Okay, let's open it up again. Output ppm. There's something wrong with it. There's definitely something. We did something wrong here now. Yeah, we did not take the canvas height into account here and subtract it from this, so we didn't inverse the Y, and so it looks this kind of strange. So let's do this again. And now let's open this up again, and yeah, now it looks right again. So what if we wouldn't have had that much wind? Let's reduce the wind a little bit to 2.03 maybe. Let's take a look at this. Yeah, so it shortens actually the path of our projectile quite a lot, but it doesn't blow it back. So this is quite nice actually. Yeah, I like it. So I like the results of chapter 2, and so let's yeah, maybe let's try it with a 0.02 maybe, because I want to have something that I can commit actually. So yeah, this is quite nice. You see all the different effects of the gravity and the velocity of the projectile and the wind there. I guess I like it. So status git add source bin chapter 2 git ci implemented resulting or implemented executable to render and show progress this far. Progress after finishing chapter 02, and we want this in one line even though it's too long. So yeah, let's push this and we are finished. Yeah, that was nice. Thank you for keeping up with me while I learn Rust and implement the Ray Tracer Challenge by James Buck. And in the next chapter, or the next video I'm making about this, we are actually talking about and implementing matrices, because we need a lot of different mathematical calculations regarding matrices in order to calculate all this different stuff later on. To, for example, transform our world, transform our objects, like moving them in space and positioning them somewhere or rotating them, and essentially everything which a 3D renderer, ray tracer, however you might implement it, like a projection-based renderer or even a ray tracer, everything that this one does is a lot of matrix calculations all the time. So we will implement them, and we will talk a little bit about what different kind of matrices there are and what you can do with that. Because by simply multiplying a vector with a vector with a matrix, we can do a lot of nice stuff we need later on. So that's actually the next chapter, which in this book, and yeah, I guess I will see you then when implementing this. Thanks again for joining me, and see you. Bye.